Our first speaker this morning is Professor Petra Döll from Frankfurt, whose work I highly admire. She is one of two teams that I know of, the other being Mark Birkens in Holland, that has endeavored to understand the global water cycle with detailed models, not just with country scale statistics or state scale statistics, but actually model global freshwaters, surface water, groundwater, flows into the ocean. And most importantly, their group has really put a big effort in understanding global groundwater resources, the dynamics of global groundwater resources, and how they have been shaped by urban areas and agriculture. Welcome, Petra. We're looking forward to your talk.
Yeah, thank you very much, Thomas, for this introduction. Yeah, for more than 20 years now, we have been working on quantifying global water flows, so both on the resources side and on the water use side, and with a focus, as Thomas has said, on groundwater and also water use for irrigation, and I think that's why Thomas invited me, as he said, and I'm very pleased to be here as invited speaker to talk about the irrigation-groundwater nexus at the global scale, so very large scale. So that we talk about the same terminology, I think it's very difficult in groundwater and also irrigation that everybody's at the same page regarding terms. I brought with me a conceptualization of the irrigation-groundwater nexus. So you see here, that's the way how we model it also in our global scale model. So what you see here in the light blue colors, they're the natural flows, the flows that would exist without irrigation, precipitation, actual evapotranspiration, groundwater recharge, and then very important also base flow. And you see here base flow is already a mixed color because as soon as you start with the anthropogenic flows, these are the water abstraction from groundwater, the water abstraction for surface water for irrigation. And then part of that is evapotranspirated, the consumptive use, and part of it is recharged. And that, of course, then again also has an effect of the base flow. And in my talk, what I want to do, I will strictly talk about water quantity, so water flows, no water quality, no impact like on food production per se. That's what Karen is then later talking about. So just about the quantification of these flows, and then first of all on the uses, and then also what these use what impact these uses have then on resources. So I'll start with showing you what our model roughly does. It's the Global Water Resources and Water Use Model WaterGAP, and it has been developed since 1996 at two universities that I worked at. And so this model WaterGAP is a water resources model in that it has a hydrology model, but importantly here we have 5 different water use models that try to estimate water use at the global scale in the sectors irrigation, livestock, domestic water use, manufacturing, and thermal power. But here we don't model yet if the water comes from groundwater or from surface water. That is then done in such a intermediate module. And then these net abstractions from groundwater and from surface water, they are then, so to say, they affect the hydrology. And when we go back to the net abstractions here, what do I mean with that? The net abstraction from groundwater is the water withdrawal from groundwater minus the return flow to groundwater, but it's the return flow both from surface water irrigation and from groundwater irrigation. And this is just a sketch on how we do the hydrological modeling. It's a row of storages. These are then the storage components that when you add them up, they should somehow fit to grace. And you see here also that we subtract water use from these different storages here. So, and just to give you an idea of the spatial scale, we work at a half-degree resolution like most of the global hydrological models. That means 55 by 55 kilometer at the equator, and that would be the picture and drainage direction map for North America. So it's about quantification of the irrigation-groundwater nexus in terms of flow now. So on the one hand, we have to somehow compute, estimate the water use related flows. And how do we do that? For irrigation, not for the other sectors. I will not touch upon those. So we first compute the consumptive water use of irrigated crops. Based on that, we compute the water abstractions from groundwater and from surface water. Then we have to come up with some estimates of the return flows. And then finally we get the net abstractions. So quite some steps. And then on the other hand, water resources related flows, we compute natural groundwater recharge. And then we also, with a balance equation, the base flow as affected already by groundwater use. Now you say, okay, we compute that. What I would like to share with you is not just the results of that computation, but I want just to give you a feeling for the many uncertainties that come into these many steps that have to be taken for 67,000 grid cells globally that we have to cover. And then we work on with daily time steps, so you can imagine that a lot of data, but also assumptions come in. So first of all, what are the uncertain data and assumptions used to compute irrigation water use components? First of all, and most important, where on earth are irrigated areas? And we distinguish areas equipped for irrigation and areas actually irrigated. And we have been working together with FAO since 1996. And together with FAO have derived various versions of the global map of irrigation areas. This is the newest version. And also together with FAO, we in particular is my colleague Stefan Siebert, worked on, so what of these areas for irrigation are equipped for groundwater irrigation? And from that, we then compute groundwater use. That was also in cooperation with FAO. I forgot to put it on, but very important. Okay, now you know, but I can tell you the uncertainty is very high where really irrigation occurs. Then you have to say something about what are the crop calendars. The climate data are very important, depends a lot on climate data, and I will show you the uncertainties quantitatively that come out of that. Then it's not so clear even what equation you use for computing potential evapotranspiration. That makes a difference. And then we have a paper in 2014 where we somehow back calculate or back estimate the degree of deficit irrigation in groundwater depletion areas. We look at actual groundwater depletion and what our model computes, and from that we sort of back calculated that. And then you don't know very much about the ratio of consumptive use over abstractions, because I said we compute consumptive use based on the area and based on the climate and so on, but then you have to assume something. And then also regarding return flows, you have to assume something. And we also made a map of drained area, so percentage of drainage, and we assume that where you have more drainage, then you would have more return flows to the surface water. Okay, and then, of course, on the water resources side, there are uncertain data and assumptions. And very important there is the surface water groundwater interactions. You don't know much. Also, again, climate data, equation for computing potential evapotranspiration. But then you have to compute actual evaporation and the runoff. What we do is we calibrate our model to long-term averages of river discharge to somehow constrain the runoff. Because otherwise, precipitation data are faulty and so on. The model is faulty. You could be very much off. So that's why we calibrate that. And then when we talk about groundwater resources, you also then have to come up with some algorithm to distinguish which flows go to the groundwater, which part of the runoff goes to the groundwater, and which flows goes directly to surface water bodies. And we do that in an heuristic way as a function of the relief, the soil texture, the hydrogeology, and if glaciers and permafrost exist. Okay, so what are results regarding first irrigation and now total water use? Maybe this is a little hard to grasp at the first moment. This is global human water use between 1900 and 2010 for all the 5 sectors that we consider. And in the darker colors, we show the return flows, and in the lighter colors, the consumptive use, and they add up to the withdrawal in this sector. And so you see here this is everything outside of irrigation. You saw here leveling off, the return flows, for example, here for manufacturing use. And this part is irrigation, the consumptive use for irrigation, and the return flows, and you see they continue to increase. Now let's look at groundwater only in a spatial distribution. So this is then only irrigation water abstractions for groundwater, because that's what the topic is today. And you see the spatial distribution that mainly shows where the irrigated areas of the world are. So you will always see in the next slides a relatively similar spatial configuration with a major, you see here the major, oops, sorry, we go back here. So the largest groundwater, the largest areas, irrigated areas that are equipped for groundwater irrigation are in India with 39 million hectares, and then China and United States with approximately half each of it. And then the rest you see is scattered all over the world. But these are already irrigation water abstractions as computed by our model with the many assumptions we put in. And when you look more carefully, you see what you want to see, I hope, in the United States, Central Valley, High Plains Aquifer, and the Mississippi embayment as the main irrigation water users. And then you see in Europe, you see the Mediterranean, and in Africa, when you saw the movie yesterday, they talked about Morocco. You see here a lot. Okay, so with this type of modeling, you can ask, for example, the question, how important is groundwater as a source of irrigation? No? You could use surface water or groundwater. And this shows the irrigation water abstractions, we're still at abstractions, from groundwater in percent of total irrigation water abstractions. And the blue areas are those where groundwater is a very important source for irrigation. I think you can look around yourself and see if you see surprising areas or not so surprising areas. But you see, I mean, that groundwater is, for example, unfortunately you don't see very much on these colors here. You see that there's a lot of irrigation down here in southeast China, but there really groundwater is not important. But really in most areas groundwater is an important source for irrigation. On the other hand, you can ask how important is irrigation as such as a groundwater user. No? So the sectoral question, and this again, this here shows irrigation water abstraction from groundwater in percent of total water abstractions. And again, the dark blue colors mean more than 80% of total water abstractions is for irrigation. And of course that shows you also, imagine you wouldn't have any irrigation, then in those areas that are blue you would barely have any groundwater abstraction or very little interaction. So it shows the importance of irrigation. I mean, we know that for global water. So let's now look at the net abstractions. These are still withdrawals. And net abstractions is, again, net abstraction from groundwater, withdrawals minus return flows. And we published that, a similar picture. This is with our newest model version in 2012. And when I saw this for the first time, I was really surprised. So let's just focus on the one above. These are the net abstractions from groundwater. And everything that is in brown is really net abstraction, something water is net taken out of groundwater, but all the blue areas are those areas where groundwater gains water because there is a return flow from irrigation from surface water. And you see large areas of the globe where you don't, by irrigation, you don't lose groundwater, but you gain groundwater. I think this is the important point to say. And definitely, I mean, you recognize the areas with a lot of groundwater abstraction. Of course, then you really lose, like here. But then, like here in this part, at least according to a model, you gain. And also, again, here in China, you gain. I mean, there's something going in. And now, it's not very meaningful, but it's always interesting to add up over the globe. I mean, it's not meaningful for management. You better look at those maps. But still interesting to look at global values. When you add up the global value for net abstractions from groundwater, it's a negative value. That means irrigation, at least according to our model, puts in more water into the groundwater than it takes out. While this is net abstraction from surface water, I mean really you take something out of surface water. Okay, let's look at this consumptive use for irrigation. We, in our model, or in this model run, we come up with a total consumptive use of 1,100 cubic kilometers per year. This is for the time period 2003 to 2009. And I would just like to take the opportunity to talk about uncertainties. When we have 3 different global climate data sets. They are more or less in equal quality, and that would change this value of 1,150 by approximately 60 cubic kilometers. So that would be just the uncertainty related to the climate model. And then other people also compute consumptive use, so the total consumptive use from irrigation. And when you look at all the values, you come up to a range between 1,000 and 1,500. So, but I would say that this 1,000 to 1,500 is not the total uncertainty, because all of the models use the same map of irrigation areas, the map that we developed together with FAO. So you see, I mean, the uncertainties are high, but they don't look as high because people use for the most important thing, they use the same data. Okay, impact of irrigation on groundwater. Irrigation with surface water, we said we have an additional recharge, but what are the impacts of irrigation with groundwater? Of course, we have an initial decrease of groundwater storage and a decrease of base flow. This is environmentally very important. And then we may end up with a groundwater depletion if the groundwater recharge, or an increase in groundwater recharge and a decrease in base flow, cannot balance the water abstraction. Then we get a groundwater depletion with continuously declining water storage. And I first want to show you the impact of human water use on base flow. This is for the period 1980 to 2009. And what you see here is the base flow with human water use as a fraction of the total natural groundwater recharge. So if humans would not interact with the groundwater, everything would be gray, because gray means, sorry, do you see anything here? I'm not sure. I can see it from here. Everything gray means that you more or less, your base flow on the long term is the same as the groundwater recharge. So, and all the areas that you see in brown are the areas that in our model we compute that they really have a groundwater depletion, that groundwater has depleted so much that there's no outflow to surface water anymore. And in blue you see the areas where, due to irrigation with surface water, more base flow occurs. And this picture, when you look at the spatial pattern, is very similar to a picture you could draw an indicator for groundwater development stress for. So what you see here is mean annual net groundwater abstraction divided by mean annual natural groundwater recharge. And you see again always the same pattern. These are the dark areas with a very high groundwater stress are those just with a lot of irrigation. That's how it is, even though this considers all the groundwater abstractions, but they are just so dominant. I mean, groundwater abstractions mainly come for irrigation. And then, as a last slide here, I show you a map of groundwater depletion by human water use between the year 2000 and 2009 in millimeter per year. So again, you find the areas that you know where groundwater depletion occurs in the United States, for example. But this looks different from, for example, what you would see from GRACE. Not only because we have, of course, it's a model and GRACE is some other type of data, but this, we used our model to take out the impact of climate variability, because GRACE over 10 years, if you have just, you're in a period of declining precipitation, maybe just for natural climate variability, will show a decrease in water storage, but that doesn't mean that it's due to human water use. It can just mean that precip has gone down. So what we do is we run our model with human water use and without human water use, and what you see is just the difference. So here you really see the areas that are caused, the depletion is caused by human water use. Okay, and almost final slide. with our modeling, we also find that irrigation accounts for 18% of the total. That means blue and green water use for crop protection, and when in groundwater, more or less for 7%. So if all the irrigation by groundwater accounts for only 7% of the total water use in crop protection. But you see how much, depletion there, of course, and so on. So I think it's very informative or mind-opening when you compare it to values that have been computed in a very recent study by Mika Jalava. Jalava, it's J-A-L-E-V-A. It's a mistyping, Jalava, J-A-L-A-V-A, in Earth Future of this March. What they did is they computed the effect of water use, the effect of changing our diets to what the World Health Organization recommends globally, no? And also when the food supply chain losses would be reduced by half. They computed the effect of these measures on blue and green water use. And they compute that if we would reduce the food supply chain losses by half and would change to a diet recommended by the World Health Organization, that would reduce both blue and green water requirements by more than 15%. So it doesn't mean we become vegetarians, just the World Health Organization diet. So when you compare that, of course, you can't simply come up with a management recommendation from that. You can easily see that consumption of food and our consumption patterns and the food loss patterns could make up for all the water in a way that irrigation consumes and has then negative impacts. We could maybe avoid those impacts. So to conclude, as you know, globally irrigation is the most important groundwater users. 70% of human groundwater abstractions and 90% of groundwater consumptive use. Irrigation with groundwater leads to base flow reductions, which are environmentally damaging for the freshwater ecosystems, and very often to groundwater depletion, and that also exacerbates sea level rise caused by climate change. And irrigation with surface water leads to increased groundwater recharge, increased groundwater storage and base flow. Maybe not so bad, but of course we know it sometimes often water pollution comes with it and so on. So maybe as a last provoking thought, I could say that in a world with free global exchange of food, we could avoid potentially environmentally damaging irrigation that only contributes to about 20%, and when we only look at groundwater irrigation, to 7%. We could avoid that if we reduce food losses and change our diet to a diet that is recommended by the World Health Organization. Thank you very much.
That was a beautiful sweeping overview. Is the microphone on? Here we go. So here's how we're going to do this morning. I'm going to take between 2 and 5 minutes for clarification questions specific to Petra's talk. I want to keep the more general questions and commentary questions for a broader discussion after we're through all of the speakers. So if you have clarification questions or questions very specific to her presentation, this is the time to ask. And do we have anybody with a microphone? The gentleman in the back, and please speak up, and I'll repeat the question.
Not being familiar with the World Health Organization's standards, are you talking about types of foods or amounts of foods that would be changed, or both?
Mm-hmm. Both. It's a calorie intake, but also a combination of the right amount of proteins and so on. So it's a combination of that.
On your third bullet point there, you have irrigation with surface water leads to increased groundwater recharge. Are your demands changing, or are you just substituting surface water for groundwater as a source of supply? Because otherwise, I'm not sure how that would relate to an increase in recharge.
Oh, okay. It has nothing to do with demands. It's just the fact that when you use surface water, you take it out of a reservoir or a river, and you put it on the field, then not everything is evapotranspirated, but some of it goes into the groundwater, and that is what I'm referring to. It just adds additional water to the groundwater. And yesterday we also heard presentations that people are wondering now that people move from flood irrigation to drip irrigation, that then you have less recharge of the groundwater. And then also maybe in the winter that you could now in California use all the infrastructure of the orchards to infiltrate water by irrigation. That's only that. Only that.
Many thanks, Petra. Great presentation. I'm just curious, I mean, why did you use the Priestley-Taylor? Because you are in close contact with FAO. Why not FAO 56 or Hargreaves, which are performing way better than Priestley-Taylor?
I mean, we have used both Priestley-Taylor and Penman-Monteith, not Hargreaves, Penman-Monteith, where you have wind and humidity. But we just feel that the wind data and the humidity data, they're, again, so uncertain at the global scale, so we're more for parsimony, and that's why we use that.
Maybe one more question? Up here in the front, Jennifer.
Yeah, thank you, Petra. If you were to put a degree of uncertainty in your results, you showed something earlier. What would it be, more or less?
Well, I talked about what is the degree of uncertainty in the consumptive water use globally, and I said we always come up with something 1,100, 1,200 cubic kilometers per year, depending also on the climate model, the climate data we put in. And I said other modelers come up with a range of, let's say, 1,000 to 1,500. And but I think that maybe is even not the total range of uncertainty, because everybody uses the same map of irrigation. That is the point. Now, we at a very early stage have tried to come up with an estimate of uncertainty at a smaller spatial scale, even at grid cells, but this is impossible to compute because you don't know. When you look at the data of FAO or whatever we used, and we also use a little bit of remote sensing, but it's really hard to say in this grid cell they irrigate or they don't. In some areas, when you then go there, they say they irrigate, but nothing happens. So it's very hard to quantify uncertainty at a smaller than global scale.